Perfect. So we've seen that we have Tata, who's a global carrier bringing IPv6 connectivity. And we, as the RIPE NCC, we travel. I'm from the training department. We travel around the region trying to teach people about IPv6 and tell them how good it is for them to start thinking about it, implementing it in their networks. The problem I see is that we meet a lot of people who are really new to the protocol, and what we do so far is teaching them about the basics. We introduce them to the new technologies, but then comes security, because if you start implementing something new, new threats and new problems will come up. So what's the state of the internet today? We have about 2.4 billion users, 35% of the people so far. But we've seen from Philip Smith that we're bringing internet connectivity to new areas all the time. So we just have to expect that the number of users will increase in the next years. And the mobile phones are coming internet devices. We all have at least one, a phone that can connect to the internet. So we have to expect the internet to become the Internet of Things. I talked recently to a representative from the German railways. They were saying that on the next trains, on the next generation of trains coming up in a few years, they will need about 32 different IPs for every seat they have on the train. And every train on average has 400 seats. You can't do this with IPv4. Well, you could, but you just would be stopped by the technology. So there's Porsche. Porsche put sensors on their cars, and they need IPv6 to enable them to the sensors. The goal of the sensors is to be able to detect problems before they're happening. So the car has a UMTS connection to the factory, so that they know already if something is happening, something is going to break. They can tell you, stop there, go to the service, and have it repaired before it really happens. There are many other stories. I have a colleague who's building her house completely on IPv6 with the IPv6 enabled thermostat, light bulbs, IPv6 cam, and everything. So we are surrounded by things, by objects that can become internet enabled, and we need IPv6 for that. So the thing is, IPv6 has such a large address space that we can make a good use of it. If you look on the top, we're only using a /3 out of that, which means 1/8 of the total space. So for now, the RIRs, like the RIPE NCC, only have /12, from that /13, and we have enough space to, this can be confusing. We have so much space that now we're trying to make a decent use of it. If we do it wrong, we have 7 other parts of space to use for that. The LARs get to /32, which is still a huge address space. And so on and so on. The users should get enough space to be future-proof for the next 10, 20, 50 years. Some of the basics. IPv6 addresses are 128 bits. They were 32 bits in IPv4. They're hexadecimal. And every subnet should be a /64, which means lots of space. The minimum allocation size for an LAR is a /32, as we saw. So that means 65,000 /48s or 16 million /56s. This means that with a basic allocation from the RIPE NCC, an LAR should be able to keep going for about 16 million users, 60 million clients, or 65,000 clients if they assign /48s. So we have home users and business users. This is just, this is not a real indication from the RIPE NCC, but this is what's happening on the internet right now. We see that home users generally get between a /64 and the /56. And I myself am going to say that this might be wrong, because, for example, at home I have a /48 from a Dutch provider, but this is what we generally recommend in our courses to hand out to the users, about a /64 and between a /64 and the /56. So that means between 1 and 256 subnets. Why should this happen? Because you might want to have a subnet for internet, a subnet, a VLAN for video, VLAN for voice, and different VLANs for guest access points or different signals provided to the user. We make examples with fridges and any other kind of instrument-enabled devices. Business users are another kind of game. They can have from a /64 up to a /48, which means big address space that they have to manage. It means 65,000 subnets to manage for mid-sized business. What does this mean? This means that somebody has to go there and tell them, hey, you have such a huge address space, you should make big use of it. There's a guide from that was published from the NCC. There's a document that gives you indication on how to do this. And let's see. Attention, we're talking about subnets. No more talking about IP addresses. If you look back, /64, /48, we're talking about between 1 and 65,000 subnets, 1 and 256 subnets for the users. Every subnet has 64 bits of addressing space. A huge number of addresses that can be used in any single /64. Such a huge address space. And what is the other problem? Once there was NAT, no NAT was supposed to be IPv6. Why this? Because the protocol was designed to have end-to-end connectivity all the time. This is the same that we had in IPv4, but then we introduced NAT because we had to keep conserving IP addresses. We have no more of this going on IPv6 because we have enough addresses supposedly to go on for a long time. And well, somebody introduced NAT also in IPv6 because they feel confident about technology. Everybody's using it nowadays. It should work also in IPv6. It's experimental, not meant to be used in not yet, and it's an RFC. But still, it provides end-to-end one-to-one mapping, so preserving the end-to-end connectivity in IPv6. What does this mean? Let's take a simple example from a small to medium business network. We have a CPE, a router, client network, all with RFC 1918 addresses, so private addressing, IMZ with RFC 1918 addresses, and what happens is that we have NAT on the CPE. So generally, we get one address, and we net it over, we do port forwarding to the IMZ, where we keep a few servers. This is going to go away. This is an IPv6 network for a small to medium business. We have a CPE, we still have a client network with a /52 or /64, servers /52 or /64, but we have a /48 assigned. We're not doing that. So imagine we have the clients here, the clients network, have the clients directly facing the internet. They're directly reachable. What was the goal in, what was one of the functions of NAT in IPv4? Topology hiding, somewhat. Behind the NAT, you could feel a little bit safer because, nobody can establish direct connections to my clients behind that. Nobody can, if they try to do that, they end up against the router, so they'll stop somehow. It's a little bit of small perceived security, simple security. Address autonomy, what does that mean? It means that using private addresses, I can change the addresses as much as I want. I can play with that. You're not really so free again with IPv6 because you are assigned /64, 56, 48, and you have to use them because they're unicast addresses directly reachable on the internet. This is important. Global address pool conservation. NAT helped the NCC go on with all this time, the NCC and the other RIs go on all this time with the few addresses that we had available in IPv4. But we don't have to do this anymore. So what was impossible with IPv4? Verifying the end-to-end trail. There was a problem. Oh, these packets go through a NAT. Okay, so we have to analyze the state table on the NAT device and see if the NAT is correct. We have to look behind the NAT device, and it would involve lots of more work. You couldn't have direct access to the systems behind it. So if you wanted to have somebody log in on your machine to perform some management or perform other actions, you couldn't do it. You needed to go to the router, do port forwarding, and then they could access your device, your host, or whatever. Meanwhile, in IPv6, every host is supposed to have a public address, at least one, more than one, connecting directly to the internet and being accessed directly from any other host. So I was at home when they delivered my IPv6 enabled connection on a fiber network. I plugged in my computer, it worked, IPv6 worked, and then I started wondering, wait, okay, so I'm directly accessible from the internet. What does this mean now? I mean, I should put a firewall in front of it. Yep, yes. Private addresses in IPv6 are called local. They're not meant to be used for communication on the internet. They're specific for institutions that need to have private address space that's just theirs. So it's not to be used for communication to the outside internet. And this all comes up. How do we do firewalling then? How can we do this? Because we have huge address space, we have devices that want to connect to each other because, well, in the Internet of Things, you don't want the script kiddie to turn on and off your light bulbs, your IPv6 enabled light bulbs. If you have your lights in your house, or if you have your thermostat that you want to be able to reach from your app on your phone to turn it on and off, or your air conditioning, you don't want a script kiddie to get into your air conditioning system, change the temperature in your house, and put it to 50 degrees so that you're not feeling well when you get back home, and so on and so on. There are lots of other examples that we can go through. So how can we do this? We can do it on the router or the CPE, but this means we need smarter and more powerful CPEs than what we have today. We'll see that this is quite not really the case, because we'll see this in a live example in real life that figured out how to do it with the actual CPEs that we have right now. But the problem is, who's going to take care of that? The user or the ISP or the business? We need maybe additional router or firewalls behind the router that will be provided by the ISP. Some businesses already do it. It means that you have to either pay somebody to keep track of that, or you have to go through some consultant, get the hardware, maintain the hardware. It's a lot more effort. Filtering bridges are pretty much the same. The difference is that they involve kind of a different design on your network. Or you could do it directly on the host. But it's unmanageable for large scale. It could be done for servers, for a low amount of servers, but it's not suitable for small devices. It's not going to be a firewall on your light bulb. It's not going to be a firewall on your fridge. Maybe they have some security features in it, but not all of them. What are the challenges though? So you can't have static rules, so you can't go on and static rules if you use privacy extensions. What do privacy extensions do in IPv6? They continuously randomize your address so that you're not traceable. But this involves that you can't have static rules because your address keeps on changing all the time. So either you need a mechanism for updating the rules, and keeping track that this address changes, or you can't have a host per host rules. There are new kinds of attacks we will see that now, and the IPv6 implementations can be buggy. Of course, there's less eyeballs and less maturity in the code than in IPv4. Even though we've heard from Philip Smith that he's been doing IPv6 for almost 20 years. The implementations are still relatively new, and less eyeballs, less people reading the code, playing with the tools. So there are still edges that need to be cut down. Common mistakes. Now we'll get into how the real thing is. IPv6 should not be blocked. IPv6 is the basics of IPv6, or you should block it by specific rules. Otherwise, the risk is to disable complete communication with your host. If the host can't do IPv6, you start filtering it, no more communication, nothing's going to happen. It get an IP address. You can talk to the closer hosts, and so on and so on. What does IPv6 do? It's similar to ICMP in IPv4, plus it's needed for stateless auto configuration, so your machine can get an IP address automatically. It's it does duplicate address detection, so when it gets an address from your previous extension, it's randomized, so it has to check that no other host on the same network has the same address. So there's a mechanism for that implemented right now in IPv6. Path MTU discovery, returning error messages, neighbor discovery, neighbor solicitation with password and solicitation. These are all the mechanisms to assign IP addresses to the hosts and tell them this is your network, this is your DHCP, go get the DNS addresses from this other host, and so on and so on. Multicast discovery, and more. You can renumber your network using IPv6, telling the hosts this is the new network, forget about this is the new network prefix. The old one has to disappear in this amount of time, and they will do it. So you have to firewall somehow. You might want to firewall IPv6 somehow. How can you do that? You need to differentiate error messages and information messages. There's an 8-bit type field in the header in an IPv6 packet. If it's from 0 to 127, the value contained in the header, this is an error message. If it's between 128 and 255, we have an informative message. So you might want to block the informative messages. You shouldn't be blocking the error messages. What adds to this whole pile of features finding IPv6 is that any of those features can be used and promoted using different kinds of addresses. We have link local addresses, which are supposed to be only on the local network. They're not supposed to be used for communication outside. We have global unicast, the normal public IP addresses that we're supposed to use on communications on the internet. Multicast, special set of addresses. It's used for as an IPv4 for multicast communication, but this works a little bit differently. You have to join a group, and to join a group, you need IPv6. ULA in particular cases. ULA only in closed environments. So you have generally on a host you have at least the link local address and the global unicast address, and then maybe a few multicast addresses. It's another story. So we have link local, global unicast. In some cases, we might also have ULA. So we have 3 kinds of addresses, all with different scopes, all using IPv6 to communicate with the network. So we have to build on top of that. They can all be source, address, and destination. But if we want to do real good filtering, we have to keep track of who can talk to and what group of addresses they can use in this environment. And if this group of addresses can talk to the outside hosts or not, if they're supposed to talk to the neighbors or not, and so on. Remember our simple network? We have a 65,000 networks, VLANs that we can create. Yes, we have to bring IPv6 on top of this, on top of the different kinds of addresses, on top of this simple network with many subnets. So a rule set can easily get complicated. Now let's see how the attacks and threats are. What can you see on IPv6 happening right now? Denial of service using IPv6. You can have your neighbor cache filled up with requests, filled up with data, so that the router stops answering to other requests, and this is a denial of service that can be caused using IPv6. Renumbering attacks, as I said, the same mechanism that I could use to renumber a network could be used by somebody else from outside the network to tell my hosts, get this new prefix, and they will do it. You can get in the way of IPv6 error messages, intercept them, do them in the middle, send different ones outside to the rest of the network. But this is not new. You could also do it like before. Security considerations is that also anybody can claim to be a router. So I could have software running on my laptop, announcing to, hey, I'm a router. This is a prefix on the local network. Send all the traffic to me, and I'll forward it to the internet. This is another kind of manipulation. But you can use REGuard to filter unauthorized targets. There's secure neighbor discovery. The problem about secure neighbor discovery is that its implementation is very hard, so there's not yet one. There's a half implementation for FreeBSD, but it doesn't work, it's broken, and it's old. So there's lots of work that still has to be done. The goal of secure neighbor discovery is to create a local certificate authority using certificates to exchange IPv6 messages so that we're sure that who's sending them is the person that's supposed, is the host that's supposed to send them. But this, as I said, it's a hard implementation. There's not yet one working on. You could leak route advertisements. Cisco enables RA by default. You can see them. You can see lots of them also on internet exchanges happening. Carriers or providers connected to an internet exchange sending RAs on the local network. This is a common mistake. It might happen. The problem is that many operating systems will just accept it and go, okay, this is still local network messaging traffic. It's fine. And sometimes you can easily get IPv6 this way. The big threat today, by the way, another big threat in IPv6 is human error. Lack of knowledge, lack of training, typos are very common, and you have to maintain the protocols. And in addition to IPv4, you have to maintain IPv6, which is going to be more work. You have to keep it well stacked on. And also, there's already pollution in IPv6 space. For example, on Red Clouds, by managed showing that there's already scans and lots of other internet pollution going on in IPv6 space. So we already have to take care of that. Second example, how do people do it? We've seen the different threats, the different problems, different challenges that we have in IPv6. So how do people do it? Swisscom deployed IPv6 on its network. They had no major complaints. They used a transition mechanism, so they can also, so the users can still get to the IPv4 network. And they also published a draft with guidelines on the security they implemented. Security guidelines. It has 4 basic rules. No traffic to and from bottoms. They drop traffic in and out of known ports, so SSH, HTTP, SMB, and there's another on the list. All initial TCP packets are regulated. So, and they have specific IPv6 rules. Apart from the last point, if you think about it, it's pretty similar to what we have in IPv4 in their case, because they're all still dealing with IPv4 main network. But as we move on, we should think about specific rules. This draft document will get more attention and will get edited by others to implement more security features. So just from experience so far, as we've heard, no noticeable increase in support calls. So far, so good. My conclusions are, presentation is meant to be a starting point. As I said, we travel around the region telling people about IPv6 and how nice is that, why they should use it. The thing is, they start implementing it, and at one point they will face the problem about security. And security is not yet seen as critical because there's supposedly very low traffic. Traffic is increasing, traffic will get a lot higher, so we need to get ready for that. Questions?
Hey, I'm Josh speaking as a random IPv6 guy from a web community, not with my Python hat on. Can you go back to one of the first slides when you recommended prefix delegations?
Yeah.
Okay, yes, this one. So, with all due respect, the rest of the presentation is brilliant. It brings lots of knowledge to the IPv6 security issues. I think this one is harmful because it recommends the prefix delegations from /64 up. So, to give you a bit of the background of the context to my comments. Some time ago, we increased the size of the allocation size, the initial allocation size in IPv6 to /29 without the additional documentation. That's from Towns Majority and myself that did the proposal. One of the main goals, initial goals, incentives was if a small ISP needs to deploy 6 RD in one 600 domain, then the only size that can be given as a prefix delegation to a user is /64, right? And this is considered harmful, because if you start deciding, if you decide that you give the user /64, then people will start inventing new mechanisms how to divide this /64 behind the CPE, proxying stuff, layer 2 stuff. I don't want to go in that direction. And that was the main reason why we started thinking about increasing the allocation size. And now I see that RIPE NCC is recommending from /64 to /56. No, wait, hang on. I spent 20 years in operations running big networks. And you know what operators think from the IPv4 understanding? Oh, so if RIPE NCC says that /64 is enough, then I'm going to do it for home users and for business users. Current best practice is /56 for home users and /48 for business users. My personal opinion is /48 for everyone.
But this is what I said.
Think about it. Think about when people see /64 to /56, what they think in their heads. Thank you.
But this is the I said a disclaimer when I was talking. Disclaimer. This is not what the RIPE NCC recommends. This is what I see is happening in the wild. So when we give our courses, we generally tell them to give a /48 for businesses and down to 56 for home users, so that they have 256 subnets. They can get along with them for multiple devices and so on. So
it's not actually what we recommend. It's what we tell people to use at the courses. It's a visual expression. Yeah. I knew I was going to get discussion about this. But yeah, that's what I wanted actually, is that a /64 is no more enough. It shouldn't be enough for people here. Yeah. So yeah, good. Any other question? No. There's one back there.
Thank you. Hi, I'm Philip from Data MENA. A very random question, general order. How do you see the growth of the adoption of IPv6, specifically in the region? Is it linear, logarithmic, exponential? And at what point do you think a typical LIR should start worrying more about security than about pure adoption and rolling out?
Okay, this is Max. Personally, IPv6 adoption, I see it's going very slow. So I can't make real provisions. There are people whose job is to do this. Thing is, when we go around and we give courses about IPv6, we generally ask before starting, what's your experience with it? And we see that a lot of people, we generally have around 25 people at our courses. Amongst them, we have 2, 3 generally who have experience, while the rest of the class, they have really no experience, especially hands-on. And that's why we really encourage them to come to our courses to get a kickoff from the very beginning. But this is our experience about that. So does this answer your question? Oh, hold on, wait a second for the microphone.
Thanks. It does answer the first half. The other half was, when do you feel it's time for an operator to start worrying more about security and less about rapidity of deployment?
Well, security would be one of the main concerns right after you've finished implementing your V6 network, your dual stack, or your IPv6 to the home, to the users. That's why Swisscom did it from the very beginning, but they're doing it in so far in a simple way. Four simple rules, as you could see. So far they worked out. I think the best moment would be right after you finished implementing it. The problem might be that you have to implement it and you have to teach your support to handle IPv6. If any call comes in with problems about it, you have your support to get ready for it, and then you can start thinking about security. The best case would be to just implement it as long as you implement your IPv6 core and whole network to the users. But we know it's hard. So as soon as you can.
If I can contribute a little bit here as well from Asia-Pacific experience, what I'm finding with the operators who are deploying V6, they are doing their V6 security completely in step with whatever deployment they're doing. So it's very much, if we're starting off with the infrastructure, the backbone. So when you turn V6 on the router, whatever V4 security you had in place on the router, the control plane security and so forth, any interface access lists, they're replicating them in V6. If any part of the router is facing a service, if that service is not available in V6, they're actually blocking V6 access to that service. They don't want to, say for example, it's a services LAN with, say, your name server, mail, and so forth. You don't want to turn V6 on that LAN if the actual devices sitting on that LAN can't do V6 yet. You've got all the issues with auto-discovery, auto-configuration, and so forth. So I find that the network operators are being very, very cautious with the steps that they follow through. So, you know, as Max was saying, you're doing it very much in the steps that you're doing the rollout in the network. So the important bit is get the network infrastructure done first, the security in place first, and don't just do it like, oh, I'll roll out, say ISIS and BGP, and then maybe 2 weeks' time I'll do some security. Whatever you've got in V4, you want to replicate in V6 at exactly the time you do the rollout. That's what I've seen most of the folks doing, and that seems to be very much a best practice way, certainly in Asia Pacific, if that helps.
Okay. Any other question? Okay, so thanks. Thank you.
Right.
Hooking up to what Philip said, my first step was actually disabling IPv6 on every system and then gradually switching it on. That would probably be the wise thing. Can you talk like for a few minutes while I search for my slides, Philip?
I was going to introduce you, but given you're on the stage,